Okay. First of all, before starting the session, let me first introduce myself to you and what this session is all about and what will be the medium of this session. Basically, my name is Aman, and you guys, I've been connected with the Facebook developers community or developer circle for around 6 to 7 months, and it has been really an amazing experience up here. And basically, I am first year undergraduate student from Symbiosis, and first of all, let me just tell you why I think I might be eligible to actually tell you about this topic, or why should you even listen to me. So I have been reading on quantum mechanics and quantum computing for a while, and my first research paper on quantum cryptography is has been approved by ICTIS 2020, and is also approved for publication in Springer magazine. So I think I might have a better understanding, if not the best, of this topic. So I think it might be really helpful for you guys. So the medium of this whole session gonna be English and somewhere Hindi too, because as you all guys know, we are more confident to explain stuff in Hindi, right? So yeah, and first of all, thanks to Nitish sir, Sangeeta Di for giving me this opportunity to actually present you this whole session. So let's first have a walkthrough of this whole session, the whole brief, like what this session is about and what we're gonna discuss in this whole session. So the main motive of this session was to actually explain, as we already saw, Nitish sir's whole upcoming live session, whole live session is to be presented in front of you, and that will be all upon quantum algorithm and all kinds of complex quantum operations that we perform on a quantum computer, if not in real world, but in theoretical manner. So before diving into those complex quantum algorithms, we first need to understand what is this quantum computation. Is it something completely different, or first of all, what is this quantum world? As wherever we see there is written quantum somewhere, कहीं भी हम देखते हैं, like there is quantum written. So we have an intuition that it will be something like science fiction, Star Wars का ship आएगा and will pass through a portal and all those weird stuff. So it is considered to be to be one of the most weirdest part of physics. And also when we actually so quantum physics came, and then mechanics, quantum field theory, now we are focusing much upon the quantum technology, that's the quantum computation. So people have the same intuition over here also, that is going to be everything going to be weird. Like एक सबसे बड़ा wrong intuition जो सबसे पहले हम देखते हैं, the bits can be in both 0 and 1 state. So these are the things that are actually there to actually first understand what's going on and then start working over it. So first we'll understand the quantum world, then we'll try to understand what is a valid data representation. When you're using a computer, it's complete logic. Okay, so you have soft logic, but at the very hard, or at the very core of it, it's pure physics. Everything, each and every part of a computer system that's working is physics. It has electricity, it has transistors and all the stuff, and all of them are physics. So there are physical laws that are actually governing the whole data mapping of your computer system and all the logics in your computer system. Now the next thing is we have been using classical computers lately for a long time, and also as we are up here in this session, we'll first discuss what is a quantum computer, how it is different from a classical computer, and that's it's more like a norm or a paradigm or a culture kind of stuff to actually first introduce quantum computers, and then we try to understand what are the physical phenomena it works upon, or what is superposition, what is entanglement. These are the two quantum mechanical phenomena it actually work upon. And then we'll try to understand what's the difference between bit and a qubit. and that will complete our first theoretical fundamental part of this whole thing. And then we will jump towards quantum hybrid algorithms, how they are created and what is the proper interpretation of it. Then we will understand or try to have a geometric interpretation of a qubit, what is a block sphere, how we actually understand the state of a qubit using block sphere. And then we will then go towards the mathematical part, which is the primary focus of this whole session, is about derivation of matrices, matrix form of quantum gates. So we'll be discussing three gates over in this session today: X gate, that's the NOT gate; H gate, Hadamard gate; and the C NOT gate. And then we will also try to prove the statement or the first protocol that we have in quantum systems, that each and every quantum gate should be reversible. So we'll see if the metrics, if the derivation that we got from having all the mathematical calculation, and then we'll see if those matrices are actually reversible or not. And then we will try to understand a simple quantum algorithm in three different ways. And I guess that should be enough for anybody to actually start their career as on, or maybe if you're an enthusiast, start studying more on quantum computation and understanding it far like more better, rather than just having a science fictitious image of it and just thinking it's quite weird and everything that is happening is uncertain and all this stuff. So there are quite strict mathematics that it follows, and it's not that weird as we actually present it, or most of the science blogs or the technical blogs present it. In this session, we'll be using few tools. So first of all, to solve the mathematical problems, so it's going to be a few complex matrix problems. So I'll be using MATLAB for doing that, because doing those calculations by hand would take maybe an year or so. So we'll be using MATLAB. And then we'll also be using IBM Q Experience, which is a nice platform for cloud access of quantum computers via cloud. We'll create a small algorithm over there, a hybrid algorithm, and then we'll see, and then we'll have an interpretation of it. And there are a few mathematical stuff that we're going to talk about. Of course, linear algebra is involved. That's the very important stuff, and it is a prerequisite if you actually want to understand this better. It is not mandatory, because I'll be explaining stuff, but recommended if you have a bit command over linear algebra, and also some probability we're gonna talk about. So yeah, guys, there's gonna be a bit more mathematics, not a bit, a lot of mathematics over here. So it can get quite boring, but I assure you, I will try to I'll try to make it more interesting by actually talking about those science fiction stuff that we come across, quantum mechanics and all those paradoxes. And actually, I think that is quite interesting from my perspective. Now, so that was a brief about this session. So let's start with our very first topic. Now, before diving into quantum computation, we first need to understand the whole span of the whole span of this industry, or of this community. So or the field of study. So a broad scope of it is quantum physics. Quantum physics is a bit different from the classical physics that we see in our day-to-day life, because it is governed by some different laws, and it's quite controversial that which theory should be actually considered as the dominant theory, because the classical physics is not true when we actually see it on small, or the very subatomic particles, while the quantum physics laws are not actually quite applicable or provable when we actually apply them over the big bodies like the solar system, or the planets and the suns, planet, sun, and all the stars, all the stuff. Now this whole quantum physics is now divided into three broad domains. One is quantum mechanics. So it's not, quantum physics is actually not quite derived. Computer science is not quite derived from quantum physics, but I need to actually show you how we actually come to the quantum information stuff. So it is divided into quantum mechanics and quantum field theory. Field theory is not what what we are interested about right now, but it is an interesting topic because quantum mechanics is right now quite saturated, and the active research is going on quantum field theory. But when you come to the quantum information, there are three major domains of it. One is quantum mechanics, the second one is computer science, and the third one is mathematics. All these three broad domains actually create the quantum information stuff, and the mathematics and quantum information creates quantum computation. So there are quantum mechanical models we need to interpret mathematically and use computer science logic or computational thinking over it to actually perform a quantum computation. So that was a quite brief introduction to this whole field, and now let's go to the very fundamental part of this whole system, a quantum particle. So whenever we say quantum, what does this word eventually means, or what is eventually a quantum particle? So this whole field of quantum physics came into existence after we found out the wave particle duality of every particle in the universe. So it was, I guess, De Broglie who actually framed out an equation and said, I won't go into the electromagnetic these all those electromagnetic stuff and the electron emission stuff. But what his whole theory was that every particle in this universe, or every body in this universe, has two kinds of nature. One is wave and one is particle nature. So a quantum particle is any particle that shows its dual nature very prominently. That means it is very easily the wave property of that particle and the particle property of that particle or the whole system is very prominent, and we can actually observe them. So for that, if you have a bit of knowledge of physics or the wave particle duality, which I don't expect, or just take my word over it, and further you can research over it. So they need to have very small mass to actually have a prominent wave function, or more like a wave kind of nature, a prominent wavelength, so that we can actually observe it in its wave form. And they should be super cooled and isolated so that we don't actually provide any external interference over it. So quantum particle is a particle whose wave and particle nature is quite prominent. It is very small, subatomic, it is super cooled and isolated. So a particle that is constantly being observed is also not quite a quantum particle. So it needs to be isolated to actually be a ideal quantum particle in the whole system. Now, that was one way of presenting what is a quantum particle. Now, let's understand what is a valid data. What is a valid data, and how do we use physical phenomena to map those values of data? So what we use in our computer system is binary presentation of data, that is 0 or 1. Matlab, it's more like we represent the whole values, like the numbers, the digits, or when you see a whole machine learning model or a whole deep learning or big data in just 0 and 1. So it is a very crucial point, or a very important fundamental structure of the whole data, the binary bit, or 0 or 1. So any physical phenomenon to be eligible candidate for representation or mapping of data should actually have a binary observation. Just for example, in our classical computers, we use transistors, and in those transistors, we use a range of potential difference to actually map out if it is 0 or 1. If it is in a particular range, the potential difference across a transistor is in a particular range, is mapped as either 0 or 1, and if it is not there, it is mapped as either 0 or 1. So it completely depends upon you how you actually want to map it. So any physical operation or any physical phenomenon that actually has a binary observation is actually eligible for representation of data. and also it should be feasible. You cannot just devise anything, any observation that is that shows that is binary into a data. It should be feasible and applicable. Now, after this, so if I'm going too fast, you can just tell me, because I don't want to delay the derivation part, and I hope I am audible. Yeah. So I don't want to delay the derivation part, so I am actually going quite fast, so with this theoretical part, so that you guys actually don't get quite bored. Now, let's discuss what is a quantum computer. So if you see the definition of a quantum computer, it is clear. It is very clear. You can just Google the definition anywhere. What is a quantum computer? You'll get a definition that a quantum device that uses quantum phenomenon, that is the superposition and entanglement of a quantum particle or system to perform meaningful operation or computation. So a device that is actually using a quantum system or a particle that is a really, really small particle or a really isolated and super cooled system, and their quantum mechanical phenomena of, or the quantum phenomena of superposition and entanglement to actually perform computation and meaningful operations. So any kind of arithmetic or logical operation comes under meaningful computation or operation. So we use these two phenomena. Now, okay, let's cut some slack and understand what is superposition and entanglement. These two are the most important and interesting phenomena of quantum computation. So let's first go towards superposition and then we'll see entanglement. Now, superposition. So what is a superposition? If you ask me, I would say a superposition is a fancy word for uncertainty. Now, why? To understand that, we should first understand two theories very well. One is wave particle duality, which we already talked about. That a quantum particle is a valid any particle is valid quantum particle if it has a prominent wave particle duality. Now, as you can see, I have shown a small diagram over here with a really cool guy with a goggles holding an electron source and emitting electrons out of it, and there is a screen towards which the electrons travel. Now, while the electron is traveling in the space or in the medium or just space, it is showing a wave like propagation. Okay, that's the wave nature of that electron. But once it reaches to the screen, and when it strikes the screen, what we see are discrete dots. Okay, if we are using one electron particle at a particular time and not just throwing bunch of them, we are seeing discrete dots on those screen. Now if we can actually see a dot on a screen, certainly it needs to be a particle, because if it was a wave, you should have rather like created a whole what to say, pattern over it, rather not a simple dot. But when we actually see a bunch of electrons thrown towards the screen, while they are traveling, we see an interference that is being generated by them. So this shows that the electrons, while they were traveling in the medium or in the space, they were acting like waves. But once they strike the screen, they're acting like particles. So this is the duality of the particle. Okay, duality of that whole of that particle or the whole system. Now, that was one theory, and the second one is uncertainty principle. As I said, it's a fancy word for uncertainty. By uncertainty, we mean something that is not quite certain, and that is very nicely defined by the uncertainty principle. So Heisenberg actually found out this whole uncertainty principle, and what he said, to predict the future or future behavior of any system, we will actually need to be certain about its position and the momentum. And once we are certain about its position and the momentum, we can predict its future position by having all the calculations, future position of that whole system by doing all those calculations. But the reality is, we cannot be actually precise about both the position and the momentum of that particle of any subatomic or quantum particle. Now, what does that actually mean? So it is so this one is the famous uncertainty equation that we see. So here delta x actually, so I tried a lot to actually cut out those physics part a lot from the like I cut out a lot of those equations, like the wave function equations and those Schrodinger's equation, and but these were a few small equations to which I could not actually remove. So just bear with it and just try to understand it. It will be quite interesting. So this delta x actually shows the uncertainty or uncertainty of the position of that particle, and delta p shows the uncertainty of the momentum of the particle. So there is this nice experiment that we actually devised, or we can actually see, is that we took a laser source and we are throwing and we are focusing a laser through a small slit. Okay. Now, what is a slit? A slit is an setup like this. So there is this like opaque obstacle, and there is another opaque obstacle, and there is a small gap in between, and the laser is allowed to pass through this gap. Now, what we see, and there is a screen over here. Now, what we see, when these two are like normally this much apart, or like quite nicely apart, so that the laser actually passes through completely, you can see a small dot as we see when we throw a laser on the wall. So we are seeing a small dot on the screen. Now, what we do is then slowly start decreasing the space between the slits, and we start contracting it more and more and more. Now, once it gets smaller and smaller, what actually we do is we are decreasing the uncertainty in the proposition. So basically, as we keep on decreasing this size of the slit, we are actually not allowing too many particles to actually go through it. And so if a particle if let me show you, if this is a particle and its position uncertainty is this much, and by narrowing the slit we are decreasing the position uncertainty in this way. Now, since the position uncertainty is actually decreased, with this equation you can actually see the momentum uncertainty is inversely proportional, which means if it is decreasing, the momentum will increase. That means the electron passing through the slit has like a higher possibility of going this side, or having a change in momentum, or uncertainty in its momentum, or a spread, or it's more like spreading in the whole space. So what we see in the observation, as we keep on decreasing it, this small zone where we are actually seeing where we were actually seeing a dot, starts elongating, and the whole light starts to spread. This shows that the photons that were passing are now having more uncertain momentum, and we cannot actually predict which photon is going to strike at which point. Now, that was the uncertainty principle. It's too hot over here. Now, that was the uncertainty principle. Now, how this actually represents superposition. So, basically, to understand superposition via this, there is a very nice experiment that I actually saw while I was seeing Eden Adams. He is a professor at MIT, his video. And I wanted to explain the using the Stern-Gerlach experiment, in which we take an inhomogeneous magnetic field and we pass an electron through it. And due to the inhomogeneous magnetic field, the electrons so if electron actually gets their eigenstates, they actually deviate completely up or completely down. And then we reverse the whole setup to 90-degree, and then we start measuring it on the basis of its left or right orientation. And then we again rotate it 90-degree and start measuring it again as up or down, and there we see the weirdness of superposition. Now, but that's actually quite hard to actually explain. So what I did, I used the Eden Adams way of actually explaining this whole thinking. So think this setup: we have a particle, or say a bunch of particles, that have two properties: hardness and the color. In the hardness property, there can be two possibilities. the particle can be hard or it can be soft, and in the color it can be either black or it can be white. Now we devise two boxes. One is the hardness box and the other one is a color box. So what this hardness box actually does, this hardness box, when any particle is given to it, it actually allows the hard particles, the particles whose hardness is hard, it allows them to pass through it while throws away the soft particles. And this color box, actually when a particle is given to it, it allows the white particles to pass while throws back the black particle. Now, what we did, we actually devised this whole setup where we are actually taking an electron source, or no, sorry, not electron, the particle source, and we are giving it first to a hardness box. Second, we are passing the output of that hardness box to the color box, and lastly we are passing the output of the color box towards the hardness box again. Now first, when these particles are thrown towards the hardness box, they're arranged arbitrarily. Okay, we don't know which particle is hard, which particle is soft, and which particle is black, and which particle is white. Now when they pass to the hardness box, what is the probability that, or how many particles will actually pass through the or what will be the output of this hardness box? So for ideal condition, let's say the arbitrary distribution was ideal, and we will see 50% of the particles actually coming out as hard and 50% of the particle actually being thrown out as soft. Okay, that means we are measuring the particles based upon their hardness. Okay, now we took this 50% hard output from the hardness box and passed it through the color box. Now what the color box does, allows the white particles to come out while throws away the black particles. So again, in ideal condition, if we provided the 50% output as hard, what would be the outcome of the white part? So in the ideal condition it should be 25. It is again divided, and 25 particles, 25% of the particles came out as white, and 25% of the particles came out as black. Now again we are passing it towards the hardness box. Now my question to you guys is, first, we passed the arbitrary particles with those two properties, hardness and color, through the hardness box, and it allowed all the hard particles to come out. And then we passed the hard particles to the color box, and it allowed all the white particles to come out. So the particles that are coming out, what would be their nature? That's a question. What should be the output of the hardness box? Guys, just comment your answer. What do you think could be the output of this hardness box? Okay. Okay, fine. Sorry, I could not wait for that long. So basically, what would be the expected output? So basically, since only the hard particles passed out through this zone, this whole zone, only the hard particles came out. So what we should be sure of that all the 25 particles that came out came as an input in the hardness box should come out as hard. Okay, they should actually come out as hard, but that was the expected value. But what is the actual output? So when we see the actual output is sorry, 12.5 of them come out as hard, while 12.5 of them come out as soft. Now, the very first question was the input in the color box were the particles that were completely hard. There was no soft particles. And then the output from the color box had the hard and white particles only. And now when we actually took those hard and white particles and gave them into the hardness box, our expected output should be all the 25 particles coming out of the box and none of them being thrown away because none of them were soft. But what we actually see was half of them turned out to be soft, and that's what is weird. Now, what actually I wanted to say, a superposition of a particle in a superposition actually has a probability of being in all the positions. It is certainly not in all the positions, but it has a probability of being in all the positions, which means eventually all the 25 particles that came in as hard and white particles were certainly hard and white when they actually came out of the color box. But when we actually applied the color box, we measured them on their color basis. So this automatically put the hardness of these particles in the superposition because we were not measuring them based upon their hardness. Which means what? Which means if we measure any particle based upon, suppose it has 5 characteristics and we measure one of them based upon one characteristics, all the other 4, their state gonna be uncertain. They're gonna have some probability of having some state, but we are certainly not sure what that state is until and unless we actually measure them. Now, this thing actually was quite disturbing. Now, then how do we actually represent the whole uncertain state? We have to have something to actually form equations and everything. So it was that point when Schrödinger actually framed out his Schrödinger's equation and also invented the wave function. Now, Schrödinger himself was not sure what a wave function actually is. All the interpretation we have yet for the wave function is that it is just like any wave, but as we can see, this wave has some amplitude, okay, and the value of the amplitude is alpha, and the projection of it in the real axis or the state axis is A, and it has another amplitude where we have the amplitude as minus beta, and the projection over the real axis or the state axis is B. Now, the only interpretation we have about this whole stuff is that if we take the magnitude of the amplitude of the wave function, this wave function, the purple line, what we get is a probability of getting the value that is on its that the wave function projects on its state axis or the real axis, and so is with beta. Now, why is the modulus important? Because the amplitude can be negative but probability cannot be, so we need to take the modulus. So that is what I have written already over here. Alpha square, the mod of alpha square is equals to the probability of getting A and the mod of beta square square of mod b is actually the probability of getting b. Now, when we, as we all know, when we actually add those, add all the probabilities together, it should result into 1. So now I would actually expect you guys to understand, or if I told you guys correctly and in an easy manner, superposition is just a fancy word for uncertainty. We are uncertain. We don't know what a superposition is. We know it exists because when we do any observation, we get output that involve all the possibilities. So we are certainly saying, or most of the blogs, or most of the definition of superposition, when you see, it actually says the superposition is the property of a quantum particle in which it is in all its possible state. It is certainly not true because we don't know what is a superposition and what state a particle is in its superposition. We just know when we do an observation with the laws of large number, we actually get all possible output states. Now you can you might say now, first of all, I would like to give a disclaimer. This explanation of uncertainty principle is actually controversial because light actually doesn't only behave like a wave particle but also behaves like a wave. So after passing through the slit, it actually when if we see light as a wave, it actually starts diffract I mean like refracting, and thus it can actually create this elongation of that dot effect. But yet scientists are quite contra this explanation of the whole uncertainty principle is quite controversial, in this scientific community. Now, I guess that was much more than enough about superposition. Now let's go towards entanglement. And here we have our Einstein quite confused about entanglement. And once Einstein was so confused about it, it called it spooky action at distance. Now, why? Okay, before going to why, first let's understand what is entanglement. So it is said when we actually bring two quantum particles close enough, very close enough, they actually there happens to be some kind of quantum phenomena that actually puts them in a state that we called entangled. Now, after putting them in that state, when we take those two particles apart and throw it in one corner of this universe and throw this one at the other corner of this universe, and we perform certain kind of observation on the particle that was thrown on the left corner of the universe, and the other one was on the right. If we perform certain observation on the left corner particle, we are certain that we will be certain about that same particular property of the particle that is thrown in the right corner. Which means if we perform, so if two particles A and B are actually entangled, and we throw B far in the space and A far in another corner of the space, and we perform certain kind of measurement over B, we can be certain about that same property of A at the same instance of time. Now, there can be two kinds of entanglement. One is direct entanglement, which means if we measure the state of particle A to be plus, the particle B state should also be the same. Okay, so it is the same kind of so another word for entanglement is coupling. So technically we call it coupling, but in the quantum physics industry we call it entanglement, while in the quantum information industry we call it coupling. Now, so in direct coupling, the state of both the particles are same. Okay, while in reverse coupling, if we actually measure the property of B in one of the corner of the universe to be plus, or suppose minus, A in another corner at the same instance of time should have a value plus, which is exactly opposite of what was B. So there are two kinds of coupling. later in this session, we will be seeing how to actually create both of them. Now, any doubts still here, feel free to actually comment. Now, why Einstein thought? So it's a question about it's an explanation about the EPR paradox, which I think might be quite interesting. So why Einstein thought it was quite spooky? So the thing is, when we actually perform, suppose these two particles are entangled together, maybe suppose directly entangled. Okay. Now, what we do actually, if we perform a measurement over the x-axis, we have a certainty of finding the value of state of B along the x-axis at time t. Okay, but suppose we are two aliens. Suppose I am in a spaceship and there is my alien friend in another spaceship. I am near the particle B and my alien friend is near the particle A. If I perform an operation over the x-axis and my alien friend performs an operation over the z-axis, my observation gives me the certainty of the x-axis properties of property of the particle in the x-axis, and due to my alien friend's observation at the same instance of time, it gives me the certainty along its z-axis. Now, this creates a paradox. In uncertainty principle or in superposition, we saw we cannot be certain about if we are measuring a quantum particle of its certain state or of a certain property, we cannot be sure about the state of other properties of this system. But here what we are doing, I am measuring x, so I am getting a certainty of x, a certainty towards x, and when he is when my alien friend is actually performing over the z-axis, he is getting a certainty over the state of the z-axis of both the particles. So at the same instance of time, both the particles collapse, or the wave function collapse is actually the whole wave function that we actually saw over here actually gets projected on its real axis. Now the wave function actually is a real value, so it's a point over here, so it's a real value, so that is the wave function collapse. So it collapses to give me a certain value of all the properties in x and z and x at the same instance of time, defying the uncertainty principle and also the superposition. So here quantum physics actually contradicts its own theories, and that's why many of the scientists who were in favor of classical physics said quantum physics as an incomplete theory. Now, guys, I'm not getting any question. I think either I am quite clear, or I'm just going too fast and just confusing everyone. So, any questions? Anything? Okay. I can't see the comments. Okay. 25 hard particles. Okay, I once there was an answer. Sorry, I didn't get the comment, but yeah, I already told. It was more like it should be 25 hard particles, but that output was not quite what we expected. So that's the weirdness of superposition. A bit versus qubit. Now, what is a bit? A bit is a normal data representation, or a bit is the smallest fundamental unit of data. That is a 0 or a 1. So all the data in the computer world is a bit. It is a bit or a collection of bit. Now, a bit, since it is being mapped via the range via mapping the range of voltage, so there can be only two possibilities of the voltage in is in the particular range or it is not. Okay, So if we are using, as we all, as most of you are computer science student, I need not go why it is 2 to the power n, but all the total possibilities for the qubit is 2 to the power n. That means if we have two qubits, it can be either in state 0 0, 0 1, 1 0, and 1 1. Okay, that means four possible states. That is 2 to the power n, and n is the number of bits. Okay, n is the number of bits. Now, what can now qubit is a quantum bit, and we use quantum particle or a system to actually map out its data. Now, a quantum system should have to be a valid phenomenon for mapping out data, should have two just two possible just should have only two possible outcomes. So, but when we actually see, suppose there are various forms of qubits, like we have seen people actually using the electron spin as a qubit. Now, if we see spin is the angular momentum. Now, what is an angular momentum? We know that electron is a charged particle, and it keeps on spinning. So any charge, when it spins in a circular motion, it creates a magnetic field, right? We have seen in solenoids. So basically, this spin angular momentum is the direction of its spinning axis. Now, by the Pauli's exclusion principle, we know that a spin can be either plus or either minus. Okay, but the direction of the spin can be anywhere in the three-dimensional space. So what we actually did, if we actually passed if we want to actually if we actually want to measure the spin angular momentum, we have to pass it through the magnetic field. Now if we pass it through a homogeneous magnetic field where all the magnetic field lines are even, it just passes undeviated, or the whole bunch of electrons passes in a like what's the word for it, a continuous distribution. It shows a continuous distribution, okay, and not a discrete distribution. But when we actually pass it to an inhomogeneous mixture where we bias the whole magnetic flux, we actually see the ones with a bit the whole angular spin a bit up to be deviating completely up, and the particles with the spin angular momentum to be a bit down, deviating completely down. So it gives me two eigenstates, up and down, which we'll be discussing in the Bloch sphere model of the qubits. Now, so we use the Stern-Gerlach experiment to actually map out the values of the Stern-Gerlach experiment to create the binary state of this spin angular momentums. Now, enough of how we actually create qubits. That was the theoretical stuff, but when you actually go to the very hardware level, it's not certainly the spin angular momentum of the electrons. Now, out of a bit, what could be the possible outcomes? So the output can be only one classical value. Why so? There can be only a single possibility of a bit being in 0 or 1. So the voltage, the potential difference over a transistor can be either in that range, or it cannot be in that range. It cannot be in that range and not in that range. It is actually not rational, right? So the possible outputs is only a classical value. That means at a particular time I can either have 0 0, 0 1, 1 0, and 1 1. But when we actually see the output of the qubit, that is something weird. But if you're a mathematics student, you can actually identify this whole thing as a probability mass function, and this x is actually a random variable. As you can see, it's here. X is a random variable. Now, at a particular instance, or at a single observation applied, or a measurement applied to a qubit certainly gives a single output. It can be 0, 0, 1, 1, 0, or 1, 1. It is never all of them, okay, at a single measurement, it gives either of those values. So we have already seen very so you would have seen on internet, if you ever tried to learn quantum computing, they would have said a qubit stays in all the possible states. But when you actually measure, because that is actually not provable, because I cannot say it is wrong and they cannot like prove that it is right, because I don't know what is superposition, I don't understand superposition, I just have a mathematical model it that just gives me probability. So I, being keeping myself on the safe side, would say that a whole superposition is a probability of getting a particular state, and a particle in a true superposition has a probability of getting all its possible states. So here the bit acts as a random variable, and we don't know what that particular measurement can give us. If it is a ideal superposition with equal probability. Now, what we are actually doing over here is we are taking the output, running the measurement like suppose 1,000 times, 10,000 times, a million times, and creating a whole data set. Okay, and based upon that whole data set, we are sampling data out and making a statistical model out of it. And what model? We are generating a probability mass function. With the probability mass function, if you have ever used IBM Q's experience, all the output you give is actually in its probability. So basically what this probability mass function actually said. So suppose I ran the whole algorithm 1024 times, okay, and we got a probability like this. Probability is mass function like this. Now let it be 0, 1, 2, 3, and 4. Now this probability bar over 0 tells me what is the probability of getting 0 if we run the whole algorithm single time, okay, not 1024 times, okay. Now this whole probability is due to the laws of large number, and we are certainly not sure that it will actually follow this whole statistical model, because again, as I said, this is a truly random variable. We don't know how the qubit is actually deciding its state until and unless we measure it. Now, what we can do is, if we want, so where comes the whole quantum supremacy stuff? There were few people who were actually talking about quantum supremacy over few videos I saw. So what is quantum supremacy? And Google recently announced this quantum supremacy. What does that actually even mean? So as you can see, the next point over here is algorithm complexity. So if you want to run an algorithm in a classical computer, if the complexity is on, in the quantum algorithm model of this whole algorithm will decrease the complexity exponentially. That is, it will decrease it to log 2n. Now, why is that happening eventually? As I said, a qubit can be in a superposition, but gives us the value to be as a random value. Okay, so indeed we need to run a quantum circuit multiple times before getting all the outputs, or we eventually don't know how many times we need to run. So we need to do a proper testing and sampling and all those stuff to actually get a norm of those calculations. Now, but certainly in a superposition, mathematically I would say mathematically, if we want to represent suppose sorry uh, suppose how to explain. So let's say it this way. So if we actually want to store 100 gigabyte of data, how many bits would we need? So basically 100 gigabytes, which means 10 to the power 3 into megabyte, 10 to the power 3 into kilobyte, and then 8 into 10 to the power 3, so it is 9 and 8 and 2 more, so it is 10 to the power 8 into 10 to the power 11 bits. Okay, while if you actually see over here the complexity, if you want to store 100 GB of data using qubits, it should be like if since it's 100 GB and it is around 8 into 10 to the power 11 bits. So just think it the value to be log 2 and 8 into 10 to the power 11, which is approximately is equals to 40 qubits, where we needed 8 into 10 to the power 11 classical bits. We would just need around 40 qubits. There is the supremacy. So a major motive of any quantum algorithm is not primarily to decrease the time. Okay, basically eventually if we see a quantum algorithm is tuned to decrease the space complexity of the whole algorithm, and in some algorithms just like Grover and Shor's algorithm, the time eventually gets decreased due to all these phenomena. Now that was a quite brief about qubits and how the wrong intuition we have that a qubit is in all the value has all the values, and one more thing, certainly it doesn't have the value 1.1 or 1.11. It doesn't have, because that is absurd. We already talked about what is a valid data. It is either 0 or 1. It is not 0 0.1, 0 0.111, 0.007. It is nothing like that. It is when it is in superposition, it can take the when we do a measurement, it can take the face of any of its value, but certainly it doesn't gives us all the value when we measure it. So wave function collapse just gives us a single classical output and not all the outputs. Okay, to get all the outputs we need to run the whole algorithm multiple times and make a statistical model, that is the probability mass function out of it. Now enough about the quantum circuits and all the stuff. Now let's jump into the gates and let's just start the mathematical stuff, because it's getting quite late and I'm running quite out of time. So let's first theoretically introduce quantum gates. So three gates we're gonna discuss. That's the NOT gate, Hadamard gate, and the control NOT gate. So the NOT gate, what it actually does, it just reverses the state of the qubit. So if the qubit is in gate 0, so Nitish sir already talked about the Dirac notations, and this is actually a column vector of 0 and 1. Sorry, not 0 and 1, 1 and 0, and applying an X operation over it actually changes it into gate 1, which is another column vector that is 0 and 1. Now, what does Hadamard gate actually do? So Hadamard gate puts the state of the qubit in a superposition. Now, a superposition, which means that we apply the Hadamard gate over state 0, it will put it in the superposition. That means it will have an equal probability of getting 0 and also equal probability of getting 1. Now we'll come to the point how we are getting these equations once I dive into the derivation of these gates. Now if we perform the CS gate, it's a bit complex to write over here, so I'll just skip it. I'll just say it is a 2 qubit gate. So if the first qubit state is 0, it does nothing to the one state, so the output will be the same. Okay, now if the first qubit or the control qubit, what we say is if 1 and the below 1 is in any state, so what the qubit so what CX will do is just flip the state of the control qubit. So if the target if the target qubit is 1, this is the target qubit, it will flip the state of the control qubit. That means it will turn it to be 1. So this creates an entanglement state. Now we'll see how it creates an entanglement state. So before that, let's just see a Gauss-Steer model of a qubit. So I have this small stimulation. I found it internet is quite interesting to actually look at. So basically, you see a block sphere model of a qubit over here. Now the z-axis is what we actually so it is, so this small arrow over here which you see is actually the state vector of this whole qubit. Now if you don't understand what is a state vector, so state vector is kind of a basis vector in this whole z coordinate plane. Now, why do I call it a state vector? Okay, and zero is a state vector and one is a state vector. Now, if you are familiar with linear algebra, you would be grinding your teeth right now that this guy is actually saying rubbish, and all the stuff he is saying is rubbish, because it is a linear it is a linear subspace, and certainly all the points on this linear surface, this vector is when we actually see the one vector, it is actually on the same linear surface. How can it actually be a basis vector? Now I would first try to take the liberty to say what is a basis vector. Basis vectors are the vectors that are orthonormal to each other. The first characteristic of a basis vector is that they should be orthonormal. Now, if you would have if you ever study the Dirac's theorems, which are actually another important governing theorems of quantum mechanics, they say the state vectors, that is the state vectors are 0 and 1, are orthonormal to each other. This means that they are quite independent of each other. Okay, which means I can of course consider them as a basis vector, and there is no mathematically and there is no wrong intuition that I have in my mind, and it is quite theoretically correct. Might not be so. You can think it of as, if we don't take the xy coordinate geometry and just take the z-axis as its own coordinate geometry, we can then certainly say these two are the basis vectors. But when we actually considered it as the three-dimensional geometry coordinate system, we have to then consider it as a state matrix. This is how I love to understand it. Now, again, this is the zero state 0, and this is the state 1. Now, as I said, we will be discussing few gates. Now, a block sphere model is valid for a single qubit system. We cannot use a block sphere model to actually show a two qubit system. The reason being, in a block sphere model, we actually annihilate lots of the properties of these vectors, like the angle between them, and their what's the so okay, so maybe the angle between them, and okay, what was it? Okay, I just forgot another property that is annihilate, but yeah, it of course annihilates the angle between them. Now, so it is valid for a single qubit system. So we certainly cannot apply the control not gate because it is a two qubit system. So we will be seeing the operation over the Hadamard gate and the by the or and the NOT gate. So as I said, the NOT gate, when we apply to the qubit, it actually flips the state. So let's see, if it is in the 0 state, it actually flips it to the state 1. So when I click to the X, it actually flips it to the state 1. And when I click it back, it flips it back again to 0. Okay. Now, when it was in 0, it flipped to 1. When it was in 1, it flipped to 0. Certainly, the X gate is doing its job. Now, the Hadamard gate actually puts the qubit in true superposition with equal probability. That means if we are mapping the state of a state of this vector in the z-axis as up to be 0 and down to be 1, which means if we want to put it in a superposition of having the probability of giving the both the eigenstate 0 and 1, we need to put it somewhere that is equidistant from both 0 and 1. So that plane will be our xy plane. We need to project this axis in this xy plane. That is this dotted circle that we are actually seeing. Let's apply the H gate and see if we are actually able to get the projection over the xy plane. As I applied the H Hadamard gate, you can see it is actually projecting towards the x-axis. Now the x is actually considered or mapped as plus or minus, which is not actually meaningful to us when we are actually doing some computation over it. But yeah, it actually does project it. Now as you can see, this vector is equidistant from both 0 and 1, and certainly when we actually perform a measurement over it, it has an equal probability of going either towards 0 and either towards 1. Now as you can see, there is a small circle over here, and if you see this equation, certainly you can identify it as the superposition equation, with this being the amplitude of the wave function, and this being the and giving the probability of getting 0, and this being another amplitude of the wave function with the probability of giving 1. But you see over here some weird kind of notations with E and I, and here is 0, which in if you see as equations. Okay, I just the electricity went off. Okay, let's see if we can continue. So which is certainly the phase angle of the whole vector. Now what is the phase? So since we know the whole superposition is a wave function, which means that it's a wave, and wave has its phase. So the vector keeps on rotating along the x-axis, keeps on rotating along the x-axis as the phase of the vector changes. So over here I have some vectors that actually change the some gates that actually change the value of theta, that actually change the phase. So if I start rotating it along the z-axis, you can see the phase actually changes, and this phase is a very crucial point. We call it a quantum phase, but I'm not diving into it. It's another advanced topic. We will know it later, but it is very important in quantum computation. Now it keeps on rotating, and it is the reason why we would see certain negative values in the superposition equation that we will be deriving after this. Now I think this is enough for the Bloch sphere. There are much more, like the projection of the vector using trigonometric function over the x-plane and stuff, but it's not in the scope of this video. Now that was about the Bloch sphere model. We already covered it. Now the interesting part, the mathematical part and the derivation part. So in the derivation part, we will be deriving the matrix form of x, h, and cx. Now I shouldn't be doing this, but let's first get the do a Google search, and let's see what the derivation we are doing is actually correct. So I'll go over this Wikipedia link, and we will actually on the very first place we'll get all the matrix form of the vectors. Okay, just a second. Let me just switch on the generator. Okay, sorry. So yeah, I think we are good. Yeah. So now let's dive into the whole derivation. So before diving into mathematics, let's first understand a bit of theory. So so first of all, I would like to say that any gate, any quantum gate is actually a linear transformation. So we have the basis vectors, that is actually 0 and 1. These are actual vectors. Now any quantum operation, suppose h is actually uh, linear transformation is actually a linear transformation, which means that we are actually, whenever we are applying a gate towards to a state vector, we are actually performing a linear transformation over it. Now let's take suppose the first gate, that is our x gate. Okay, now the x gate, we know, so there are two ways of actually doing it. uh, First we will see if we apply the x gate towards 0, it gives me the output as 1. Okay, and if we apply the x gate over 1, it gives me the output 0. Okay, now let's finally derive the matrix of it. Now let me name it equation 1. Okay, and this one equation 2. Okay, and 1, if we write it in the matrix form, x, and let's write 0 as 1 and 0. Okay, is equals to 0 and 1. Okay, now if we see the second equation, we see 0 and 1, which is equals to 1 and 0. So 0 converted to 1, 1 converted to 0. Now, if you are familiar with the if you are quite familiar with the linear algebra, you would see that these two are orthogonal or orthonormal vectors. Now, as you can see, sorry, as you can see, if we multiply this vector with this linear transformation matrix, since it is a two-dimensional vector, so x should be a 2 by 2 matrix. So it should be a 2 by 2 matrix. So if we multiply this vector with x, it should give me the first column of x. So certainly the first column of x is 0 and 1. As you can see, we already got the equation, so it's 0 and 1, and multiplying this transformation matrix with this vector would give me the second column of x. So this would give me 1 and 0, which is the first column, and this is the second column. So finally, what is my x? So finally, I can say my x is equals to 0, 1, 1, and 0. So let's see if we derived it correctly. And we see our x matrix. X is 0, 1, 1, 0, and what we got was 0, 1, 1, 0. So our first derivation is correct. Now, what if you would see most of the universities and the journals, how they actually do a derivation is via framing this equation. Okay, now what we do to derive the equation for x, we take the outer product of the input value and the output value and add all of the possible inputs with their respective outputs. Sorry. So we are taking an outer product over here. And how it is an outer product? Basically, this part over here is a Hermitian transpose, or just a transpose you can say in this case, or more like conjugate transpose of the vector 0. So it is more like a b dash, which is certainly the outer product. Now, so we would see x is equals to 1 and 0, and 1 is 1 and 0, plus 0 and 1 and 1 and 0. Now this would give me the result as 1 into 1 is 1. Okay, then it's 0, then it's 0, then it's 0, plus 0 into 1 is 0, 0 into 0 is 0, 1 into 1 is 1, uh, 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 I did something. Okay, yeah. So basically, I wrote over here the wrong value of 1. So it should be uh, 0 and 1. So yeah, now it is not again. Uh, mm, okay, where did I mess it up? 0, 0. Um, where did I mess it up? 0, 0, 1, 0. Okay, that's why I thought of doing it in MATLAB. So just let's do it in MATLAB. I think I just messed it up. So we would first give first we would define state vectors, which is 1 and 0. That's for O, and for 1 we would define this variable I, which is 0 and 1. So now to actually derive the X gate, we would actually have to do a cross product of all the possible outputs and all the possible inputs. So when we when we give the input as 0, what we get is the output as 1. So we will do an outer product of both of them, plus when we apply the input supply the input as I, or state 1, we get the output as 0, and we do perform an outer product of it. And finally you can see this equation, or this equation, which I certainly messed up the whole multiplication over here, which was an easy one, and it's like really embarrassing, but yeah. So I just so using this formula, we certainly derived the vector over here. So as you can see, the x vector is already derived, and we can check the value again. It's not needed, but still we can check the value again. It's the correct derivation. Now that was about X. Now let's come back to Hadamard gate. So now we will do the same thing over here. As we all know, we will take the input. Okay. Now there are two ways, as I already said. There are two ways. One is multiply all the possible state vectors, okay, with the gate, and get each of the column and then form the transformation matrix, or just frame this equation by taking out the cross product of not cross sorry outer product of the input and the output. So as we all know, when we apply the Hadamard gate, when the Hadamard gate is actually applied, so there are two possible values. One is 0. So when it is applied over it, the value is 1 by root over 2. Now you would say, where we are getting these values 1 by root over 2, Kate 0 plus Kate 1. So basically we got all these equations by actually running the whole computer system, or the whole calculation several times, and then actually sampling out the answers and then framing the equation. So basically I wanted to introduce you guys to a quantum oracle, but I thought of just letting it go, and eventually it's a very easy topic. As we go on into the quantum algorithms, we will be seeing what is a quantum oracle. Now this is the equation we see. Now if we perform Hadamard operation over 1, we see the output as 1 by root over 2 Kate 0 minus Kate 1. Again, this minus is due to the quantum phase we were talking about in the Bloch sphere. Okay, now these are the two equations. So what we are seeing over here is, so what we can see over here, I will name it as 1, and I would name it as 2. Now if you want to actually find out the whole mathematical go through the mathematical way, you can actually go, but what I would but that would take too long, so I would just frame the equation and run it in MATLAB, and just make it a bit fast. So H gate matrix is equals to 1 by root over 2. Okay, we just took 1 by root over 2 common out, and the outer product of 0 because when we supply 0, one possible state is it can give 0, or one possible state is if we supply 0 it will give 1, because it is in superposition and randomly it will give us the output. And another possibility is if we provide 1 to it, if we provide 1 to it, I'm really sorry I don't have a writing pad, I'm writing it with the mouse, so it's just clumsy, but I hope you guys are understanding it. So it would give us either 0, or it would just give us, if we provide 1, it would just give us 1 back again. Now again, this negative sign is due to the quantum phase. You can check it out later. It's quite important advanced topic, but we are not actually covering it in this video, because it is not necessary to actually get started with a quantum algorithm. Now we framed out this equation. Let's perform the whole matrix calculation in the MATLAB. Now, when we apply the H gate, the formula says, okay, we'll multiply 1 by root over 2 later. First, let's solve this whole question. So it's cross product between 0 and 0. Sorry, not cross, outer product between 0 and 0 plus outer product between 0 and 1. So it is O and I. And also the outer product of I and 0, and also and minus it is I and I. Now once we run it, we get the matrix 1 1 1 minus 1, and now we'll multiply the 1 by root over 2. So 1 by root over 2 multiplied with Hadamard gate. So this is the decimal value of 1 by root over 2. So finally we got our output as H as is equals to 1 by root over 2, and the matrix being 1 1 1 minus 1. So let's check if we actually had the derivation right, and where goes the Hadamard gate? Here the Hadamard gate is 1 by root over 2 1 1 1 minus 1. So and that's what we actually got in our whole derivation. So finally we have this linear this transformation matrix ready. Now let's go back into the drawing table, and now let's do the most interesting thing, derivation of the C0 gate. Now the C0 gate is actually a 2-qubit gate, which means it actually acts on 2 qubits, which means we'll have to actually create a new compound system that has 2-qubit complex. Now what is that? In simple terms, we need to create Bell state. And what is Bell state? You can Google it out. There is a huge long definition of it. And but I would just say Bell state is like finding the basis vectors of a compound qubit space. Okay. Now, so here we need to create 2-qubit space. So we already said what C0 gate actually does. It creates entanglement. Okay. Now when we say it creates entanglement, we mean either direct entanglement or reverse entanglement. So when we create a 2-qubit state, what we actually do to create a 2-qubit state, we perform an outer product over gate 0 and gate 0 to create one Bell state, and then gate 0 and outer product of gate 1 to get another Bell state, and then we perform outer product of gate 1 and gate 0, and then of 1 and 1. Okay. Now 1 and 1. So this would give me a vector of 4 dimensions, and we will then convert those vectors from 4 dimensions. It will give me a 2 by 2 vector, and then we'll need to convert that 2 by 2 matrix into a column matrix, so that we get the Bell state, which is also the basis vectors of the compound qubit state. Now, So I would write state 1, that is this very state. Okay, let's name it sorry, let's name it 1. Okay, the first state gonna be outer product of 0 and 0, which is 1 0 0 1 0 0 0, and now we'll convert it into a column vector, which is equals to s1. So it is a bit tricky in MATLAB to actually do a column vector, to convert it into a column vector. S1 is equals to s1, and change the dimension, and I'll just copy it up and execute it. So now it's in the column vector. So the first state of mine is, okay, let's write it over here. So the first state of mine is 1 0 0 and 0. Okay, now the second one gonna be the second vector is actually cross product of 0 and 1, which gave me this 2 by 2 matrix, and we're gonna convert it into a column matrix to get the Bell state, and it goes the Bell state. So I got my second Bell state to be 0 1 0 and 0. Now that was the, now let's create the third one, which is 1 crossed gate 1 crossed with 0, gate 0. Now we got the Bell state as this, and then change it to the column vector, which is S3, 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 and S3. Now the third column vector is 0, 0, 1, and 0. Okay, and the fourth one is cross between gate 1 and gate 2. Okay, now convert it into column vector. I think it's column vector. So I think okay, yeah, column vector. So I think I took the time of 2 hours actually, and I think it's fine. 2 hours is okay to complete this whole tutorial. It's really an important one if you actually want to get started with quantum computing. 0 0 0 and 1. Now these are the 4 states, Bell states. Now again, what you can do is take this basis vectors, multiply it with the CX matrix, and equate it with its with the possible output, and you can actually frame out the equation without actually solving out the whole equation. Or what we can do is frame out the frame out our easy equation that we always do, where if the state is 0 and 0, so basically we can actually write this state, this gate 0 outer product of gate 0 as 0 and 0. When we supply this input to the X gate, it gives me the output as 0 and 0. Now for the time being, I am taking this first qubit. This is the first qubit as the control gate. Depending upon whose value, it will decide if it wants to flip the value of the second qubit, or if it doesn't want. So it is the control qubit, and this is the target qubit. Now this equation we will add the second possible input. So second possible input is 0 1, and certainly it will give me 0 1 because control is yet 0, so no flipping. Now the next possible state is 1 and 0. Now the control is actually 1, so the output will be 1 and 1 because it flips the target qubit, plus 1 and 1. So here again the control is 1, so it will again flip the target qubit. So it is 1 and 0. Now we frame this equation. Let's run it in MATLAB and actually get it done. So this one was our state 1, this is our state 2, this is our state 3, and this is our state 4. So let me just write S1, S2, S3, and S4. Okay, now let's do it in the MATLAB. Perform the equations. So we are actually crossing state 1 with state 1. Sorry, not crossing, performing the outer product. I don't know why I'm so obsessed with cross products. Anyways, So S1 outer with S1 plus. Now we are like performing an outer product of state 2 with state 2 itself. So state 2 having outer with S2 itself, and then we are performing an outer with state 3 and state 4. So S3 and S4 plus, and we are performing the fourth outer with fourth Bell state and the third Bell state. Again, it gives me this output. So this is our C naught matrix. So again, I said all the quantum gates are actually transformation matrices. So since this Bell state was actually our four-dimensional transformation, four-dimensional matrix. So the transformation matrix will be 4 by 4 matrix. So let's see if we got the answer correct. Where is the control knot? Here's the control knot gate. One one in the last place and one in the second last place. So one in the last place, one in the second last place. Finally, we got our transformation matrix quite correctly. Now let's perform. Now let's do the most interesting thing. So what we do in a normal quantum computer, we apply apply some gates to the qubits on the simulation that IBM created and all the stuff created. Let's do it in a very computer. It might not give us a quantum answer or random answer, but it will certainly do the whole operation in a mathematical way. So let's apply these quantum gates to normal qubits. So suppose our first output. So first operation we are doing is applying Hadamard gate. Suppose X gate towards on 0. That is state 0. Now, why would I do this multiplication? Because performing linear transformation is actually multiplying the transformation matrix with the vector. We are applying the transformation on. So once we do that, now first let's see what was 0. 0 was the value of gate O was the value of gate 0, which is 1 and 0. So when we applied the NOT gate over here, what we got was a flipped answer of it. And if we see if state 1 is equals to the answer, oops. Okay, sorry, I don't know what we are doing. So basically, what did I do? Okay, so is equals. I just assigned it 0 and 1. So as we can see, we got the answer as 0 and 1, and which was certainly the value of our I, which is 0 and 1 as well. Now let's apply the Hadamard operation over this. Now let's apply the X gate over I, and let's see what's the output. And when we apply the X gate over I, we get the gate 1 answer, that is flipping the value of 0 to the flipping the value of 1 to the value of 0. Now let's apply the Hadamard gate, and let's see what happens when we apply it to the 0 gate. Sorry, not 0 gate. The 0 matrix or the gate 0 state. When we apply it, it gives me half a probability over having 1 on the top side and half a probability over having 1 and 0 in the top side. So basically, it allows me to have the value of 1 and 0 with equal probability on both the sides, which means it is actually in a true superposition. This probability or this matrix can actually result in any random value of 0 and 1. Now that was the Hadamard operation over H naught, over 0 state, and we got was equal probability. And let's see if it was what we framed over here. So yep, it is. So it is half over the 0 part and half over the first part. Now if we apply the same Hadamard gate over state 1, we get half a probability over up and half a probability over negative half of it's not negative half of probability, but half a probability of down. And certainly the phase of the vector is minus. As we see, if we apply the Hadamard gate over 1, we get half a probability of getting 0 and minus half a probability of getting 1, and so is over here. Now, that was the operation. Now, when we come to the application of C naught gate, it's a bit tricky because we first need to create the bell state. As we see, suppose if we want to apply the C naught gate over 0 and 1. So let's first dive into the quantum IBMQ experience and create a circuit to see what we, if we, to be sure of what we are doing in the MATLAB is quite correct. So now let's create a new circuit. And over here, what I'm going to do is first put the first qubit in the superposition. And again, it's just a linear transformation to this matrix, to this vector 0. And then put a C naught gate to entangle both of them. And I'll just do a barrier, give a barrier over here. So that we can actually segregate both of them. It won't actually affect the output anyways. Now if I save the changes and run them, actually I'm seeing your comments, but I think they are not updating. Yeah. So pending results. Did it run? Okay, yeah, we just got the answer. And actually I run it 2 times anyways. So let's check what the answer is. Yeah. Okay, I think it is affecting. The barrier is actually affecting. Uh, okay, let's create a new one. So a Hadamard gate and a C naught gate, sorry, and a C naught gate, and let's save the changes and run it. So think I don't know, something is actually wrong. It should not. I am quite confident it should not give this output to me. Uh, Putting up the Hadamard gate and then the C naught gate and then saving. Run 124 shots, correct. Pending result. Okay. Okay, fine. I got what's the issue. So we need to put this measurement gate. Sorry, I'm really sorry. Yeah. So okay, I was not even measuring the qubits. Fine. So yeah, that barrier should not actually affect the whole system. But yeah. So now I should get my output. Now here is my output. As you can see, of course, the first two qubits are represented in the last two digits of this whole binary output. As you can see, both of them are quite entangled, as the only possible output from the whole circuit is 0 0 and 1 1. It is not actually different. So it is an example of direct coupling. And let's create another file, or maybe I'll just change this whole experiment to actually perform a reverse coupling. In reverse coupling, what I just need to do is put an X gate to actually flip this 0 value to 1, and so that when the value of it is 0, it remains 1, and when the value of it is actually 1, it flips out and changes to 0. So it is either 0 1 and 1 0. So it is actually reverse coupling, if you see. Save the changes and run. Now, it takes a while, but yeah, it's worth it. Gives you the free access to a quantum computer, of course. What do you expect? So, yeah. So here we see the only possible outputs are 0, 1 and 1, 0. So of course they are not exactly equal, because there are random noises that actually gets created. So it's something that a quantum computer is actually facing a problem with right now, and it is nowhere in near future that we're gonna uh, see a quantum supremacy because of this very issue, until we have some advancement in material science and technology. Now, since we did it in the normal quantum computer, in the quantum simulator, now let's do it in our MATLAB and see if if we are able to generate the same output state. So before applying the C naught gate, we need to first convert the convert the normal vectors, or the quantum subsystem into a compound or two qubit system. So for that I need to actually form the Bell state. So which we have already formulated, but let's actually do it again. So basically I'm creating one qubit, what we actually do in our IBM experience, and I'm assigning it 0. Right now I'm doing a direct coupling over here, so I would use the q2 value as 1. Sorry, q2 value should be 0 because it is a direct coupling. Q1 is 0, Q2 is 0, applying Hadamard gate over Q1. So Q1 is equals to Hadamard gate applied over it. Is Q1. So we got this output, and then we need to couple both of them. So and create a Bell state. So the Bell state QB, I would name it, gonna be Q1 crossed, not crossed. Why am I saying crossed? It's outer. Q1 outer with Q2, and this gives me this state, and I need to then change the very value of QB. It's not value, very shape of QB to be in four-dimensional Bell state, and QB. I got this Bell state, and now I'll be applying a C naught gate over it. C naught gate over QB, and I get this output. Now, what does it mean? That means I have a probability of getting 1 on the first column, row, and 1 in the second row, while the middle two rows should be 0. Let's go and check are all the Bell state that we created and see what are the eligible outputs we have for it. So the middle two of them should be 0. So certainly our first Bell state is an eligible candidate for the output. Again, this 2 should be 0, but here it is not. So this is not an eligible candidate. This 2 should be 0. Again, this third one is also not an eligible candidate. And again, this 2 should be 0. And yep, it's eligible candidate. So 1 and 4. 1 and 4 were the two Bell states that were actually eligible for the output. Now, if we see, 1 is actually what? 0, 0, and 4 is actually 1 and 1. So our all possible outputs are only 0, 0 and 1, 1. That's what this matrix over here says, and that's what the IBM simulation actually says. It can be only 0, 0, the last two ones are 0, 0 or 1, 1, and no other possibility over that. Okay, now this shows we have actually done it very correctly. And now let's perform a reverse coupling. So for reverse coupling, as you can already see, I just applied a NOT gate over the second qubit. So I'll do the same over here. Our Q1 will be same, and in Q2, I will apply a NOT gate. I'll apply a NOT gate over Q2. and this gives is this flips the output, and then we will couple both of them. To couple both of them, I will take these commands. I hope you would allow me to do that. We have already done it before, so I found the outer product of both of them and then change it to the bell state, and we get this bell state. And now when we perform an entanglement over them, or or do a C naught operation over them, the output I get is the middle ones have the probability of being 0 and 1 both, and the first and the last one should be 0. Now let's come back to our Bell states and see what are the possible valid candidates for these outputs. So one of them is so this one, both of them is 0 over here. That's very correct. But the first one is 1, which is certainly not valid. The first one, which is certainly not valid. Now, the first one over here is 0 and the last one over here is 0. So it is valid. Okay, let me just change the color so that we can understand better. So it is certainly valid. Okay. And again, it is 0 over here. It is 0 over here. It is also certainly valid. And it is 0 over here, but 1 over here, not valid. So we see the second and the third. This is the second and the third Bell state is eligible output for only eligible outputs for the reverse entanglement state. So the second and third one is 0, 1, and the third one is 1 and 0. So you can see how we actually over here did direct coupling, and over here did reverse coupling, and so does says our output from the quantum IBM Q experience. It can be only 0, 1 and 1, 0, and so did we get over here. It can be only it can be only 0, 1 and 1, 0. So this is how we actually perform matrix operation, understand these gates domestic operations. Now, okay, there were these two ways to entangle qubits, and we already discussed both of them. So this is a circuit diagram for both of them, and now that was about all about the derivation. Now we would try to prove that each gate is reversible. So as I said, each matrix gate, each quantum gate is a matrix transformation or linear transformation, I would say. So each quantum gate is a linear transformation. So if we apply a linear transformation over X and we get Y, this is a normal application of a linear transformation. But when we say it is reversible, or I want to reverse the whole transformation, what do I actually do? I take the same equation, or it's more like I take the inverse of this transformation and multiply and apply it to the output. Can you guys allow me to do that? Am I correct? So it's pure linear algebra. It's nothing new. Reversing a linear transformation. It is just multiplication of the transformation inverse of the transformation matrix with the output. We'll get the final vector. We'll get the initial vector. Now, we also know a linear transformation matrix, and multiplication of it with its inverse gives us the identity matrix of that vector dimension. Am I correct? Certainly, it's pure linear algebra. When we say a quantum gate is a transformation matrix and a quantum gate is reversible, which means it is its own inverse. Am I correct? Which means what? If I apply Hadamard gate over the state X, it gives me Y, and since it is reversible, I should input Y and it should give me X. with the same gate, which means here we are applying an inverse of it, And in quantum gate we'll be applying the same quantum gate over the edge, which so let me show you like this. If we are inputting x over here, it gives me y. Okay, and since it is reversible, if we input y to the same qubit, if we input y to the same gate, h, it should give me the output x. Correct? Just a second, I think the electricity just went away. I need to turn on the generator. Okay, the generator is not on. So yeah, so let's finish it up, wind it up as fast as we can. So basically it's the Hadamard gate should, or any quantum gate should be its own inverse, which means if we multiply a quantum gate, suppose x, if we multiply it with x, it should be its own inverse, and the multiplication of a transformation matrix with its own inverse gives us the identity matrix of that vector space. It's a two-dimensional vector space, so let's see if we actually get the proper output. And so do we actually get. So we get the identity matrix of a two-dimensional vector space. And let's again check if the Hadamard gate is actually reversible. Indeed, it is. And now let's check if C0 gate is actually reversible. It is actually reversible. So hereby we proved each and every quantum gate is reversible. Now I think you guys would have understood how to actually interpret this stuff, interpret the whole gates and the transformation as linear algebra, or matrix manipulations, or linear transformations. Now another and the last topic of this whole session will be how we can actually understand quantum circuit. So basically there are two ways to actually understand quantum circuit. So let's come over here and actually understand this quantum circuit. So there are two. So there are not two. There are actually three ways. So one is the linear way. Let me just write them. One is a linear way, and the other one is using metrics, as that we already saw, and the other one is using uh, equations, that is using the bracket and the Dirac notations, the way you used to say, but actually it's rather more precisely Dirac theories and bracket notation. Now, okay, so now let's see a linear way to actually see this whole problem. So basically, if we want to see a linear way, if we take these two qubits, so suppose we have two qubits over here. So if you are a programmer, you would actually find this one rather more easy. And if you're a mathematics student or into mathematics, you find metrics one easy. And if you are a physics student, physics lover, you would find equations. It's not a hard fast rule, but I'm just saying a norm. And my favorite is both of them. So basically, yeah, in a linear way, we've actually performed a Hadamard operation over this qubit and a NOT operation over this qubit. Okay. Now, it actually then branches the possibility of outputs as 0 and 1. And this changes the output as 1. Now, we would actually apply now a C0 gate. Now, if we apply a C0 gate over 0 and 1, and another possibility is we would apply over 1 and 1. So once we perform a C0 operation over both of them, what are the outputs? The output can be will be like a Bell state, not a Bell state. It's like a two vectors, a two qubit state, which is actually 0 and 1, because it's actually the control qubit. That the first one I took is 0, and this one will be actually since this one is the control qubit and this one is the target qubit. So basically this one since the control is 1, it will actually flip it, so the output will be 1 and 0. Again we forgot the same answers, and it was a linear way of understanding the whole quantum algorithm. And then we will see, we already saw the matrix form. So we completed the linear form, matrix form, and now the equation form. Now, in the equation way, we will actually start forming equations. So as we see, let's form equations a bit fast enough. So we apply the Hadamard gate over 0, which gave me this equation, half a probability of getting both 0 and gate 1. And then we applied a NOT gate over 1, and we got the value not 1, it's not 1, it's actually 0 over 0, and we got the output as 1. Now what we did, we then actually took the Bell state and took the Bell state and performed a C naught operation. So we took the 1 root over 2 0, that's the first qubit. We will be coupling, not coupling precisely, we will be forming we will be forming a Bell state first, and then we'll be applying the C naught over it. So so for formation of the Bell state, we will actually multiply or have a outer product of this one with all the possible outputs from the first qubit, which is actually 0 and 1, and plus 1 and 1. This gives me a Bell state, and when we apply a C naught over this Bell state, we are applying a C naught over this Bell state, it gives me the output as half the probability of getting since the control qubit is 0, it will be 1, it won't be flipped, so it won't be changed, plus the probability of getting, since the control qubit is 1, so it will certainly change, so 1 and 0. And this is our final interpretation or the final result. You can see it is having an equal probability of getting 0 1 and 1 0. So which was this equation? This was the reverse coupling, and when we actually go in the quantum IBM Q, we actually saw it was quite true. It is not ideal. Whatever calculation we did over here was quite ideal calculation, but due to some quantum noises, we actually see this fluctuation, but it should have been in an ideal condition, equal probability. So with this, we actually saw or we actually